Next, we're going to talk about atmospheric effects. We'll see that we'll have to talk about attenuation, and attenuation essentially due to water vapor and oxygen, also attenuation due to rain, and then we'll have to talk about refraction. Refraction is ray bending due to the variation of the atmosphere refraction index with height. Also, it's important to notice that, of course, most of those effects are also important in approximately the first 2 kilometers of altitude, because as we increase the altitude, well, the presence of gases is smaller, and also the probability of rain is much smaller. So, we are essentially concerned about propagation in the lower atmosphere. Now, this is the usual graph that represents attenuation due to atmospheric phenomena. Here we have what we call specific attenuation expressed in dB per kilometer. And here we have a frequency scale, and then we're representing the contribution to attenuation to different factors. First we have gases, that's oxygen and water vapor, and we can see that, for instance, oxygen is this red line that has, well, very small contribution, except around 60 gigahertz, in which there is a resonance of the oxygen molecule that causes a very high attenuation. That value is around 10 dB per kilometer. When we consider water vapor, this is that dashed red line, and we can see it also can have very small values, but it has certain peaks, and there is one particular peak which is around 22 gigahertz. When we consider the total contribution to the attenuation of atmospheric gases, which is the blue line, it's essentially the contribution of those two components, oxygen and water vapor, is this blue line. And there are some important things to remark. First, notice that below 10 gigahertz, attenuation due to gas absorption is very low. We're talking about attenuations that's smaller than 1/100th of a dB per kilometer. So actually, this is very small attenuation. But at 22 gigahertz or 60 gigahertz, it can be an important factor. This is for atmospheric attenuation. But there is another component that has to be taken into account, which is rain. And here we are plotting also the contribution of rain in three cases: light rain, moderate rain, and heavy rain. Notice that when we consider light rain, which is this dashed line, in all cases, that contribution of that light rain is much smaller than the contribution of attenuation due to gases, so we can be essentially neglected. But this is not the case for a moderate rain, in which we can see that, especially at a certain frequencies, it has a higher contribution than the gas contribution. And of course, when we have heavier rain, the attenuation can be much higher. Still, rain can have, even very heavy rain, can have a very small contribution at low frequencies. So for instance, at frequencies below 1 gigahertz, rain has a very small effect. Now consider, for instance, propagation of FM radio broadcast or TV broadcast, which are below 1 gigahertz, are practically not affected by rain. But at frequencies around maybe at a frequency of 10 gigahertz, rain can be a major problem. And of course, although not present all the time, it has to be taken into account because if we want to guarantee that a certain communication system works, although it rains, that increment of attenuation has to be considered. Now, this specific attenuation expressed in dB per kilometer, can be used if, we are using a certain radio link above the ground. It has a certain distance we're covering a distance of 10 kilometers, then we just have to multiply that specific attenuation by the distance. What happens with Earth to satellite communications? Well, in that case, when we're using an Earth to satellite communication, as I said before, the effects of the atmosphere are just important in the first 2 kilometers. So in that case, what we'll use is the following graph, and here I'm just plotting attenuation due to gases. We're using what we call the zenith attenuation. That's absolute attenuation in dBs as a function of the frequency, and it tells the attenuation we can expect if I have my antenna pointing vertically towards the sky. So that would be the attenuation that I would have at the different frequencies. Again, at frequencies below 1 GHz, that attenuation can be very small, but at frequencies around 20 GHz or at 60 GHz can be huge. Notice at 60 GHz we can have attenuations of more than 100 dBs. What happens if the antenna is not pointing vertically, but it's pointing at a certain angle? Well, in that case, we're assuming like a flat Earth model, and of course, if I'm pointing at a certain angle, the distance traveled along the atmosphere is larger, so actually the correction we have to do is take in that zenith attenuation and divide by the sinus of this angle. And that would give us the overall attenuation through this slant path towards the satellite. So this is for attenuation. There is another important phenomena which is called refraction. In the atmosphere, and due to the gas content, the refraction index N is slightly higher than 1. We are not in perfectly vacuum, but because of the presence of gases, the refraction coefficient is a little bit higher than 1. Also, we know that as the altitude increases, the gas content diminishes, so we would expect that as the altitude increases, N tends to 1. Since N is very close to 1, usually people talk about another unit which is called the refractivity N, which is defined as N minus 1 times 10 to the 6. And this is measured in N units. Now, the International Union of Telecommunication defines a reference atmosphere as having a variation of the refractivity with the height in the following way, where h is the altitude above sea level in kilometers. So if we plot that refractivity as a function of the height, what we observe is that at ground level we have a value of 350. Remember that this is obtained as n minus 1 10 to the 6, so it's very close. Actually, n is very close, the refractivity is very close to 1, but not exactly 1. And as we increase the height, that refractivity diminishes. Now, refraction is caused by the fact that the atmosphere does not have a constant refractivity, but it changes with altitude. So, if we consider standard stratified atmosphere, in which this is atmosphere and we have like different slices in which the refraction index diminishes as we increase the altitude, so N1 is larger than N2 and N2 is larger than N3. Now we have a wave propagation through this medium, and of course we have a medium in which the refraction index changes, and we can see that because of that variation of the refraction index, what happens is that that angle phi1 is smaller than phi2. So actually the ray is bending as it propagates through the atmosphere. So actually the ray does not travel in a straight path, but it bends. And this is what is called refraction. And the cause, or the reason, is because the refraction index diminishes as we increase the altitude. Now, what is the effect? Well, we will not go through the math, but for antennas placed at similar height, the curvature radius of the ray, 1 over r, can be found as minus the derivative of n with the height. Now, in this sort of, for the standard atmosphere, that derivative is essentially constant, so that means that curvature radius is constant for the ray, and it can be found that for the standard atmosphere, that radius is approximately 26,000 kilometers. So now imagine we have two antennas in the Earth. The radius of the Earth is 640 kilometers. And well, we would expect that from this antenna to this antenna, we would be communicating through a straight path, through a straight ray. But in practice, what happens is that the ray is bending with a curvature radius of 26,000 kilometers. Well, and what is the significance of that? Well, imagine we have an obstacle here. Well, in order to accurately compute, for instance, if we have diffraction or we don't have diffraction, using our Fresnel ellipsoid, well, that clearance distance, actually, what we have to take into account is that our ray is bending and is not traveling in a straight line. And that, of course, gives us a little bit more clearance than we were actually expecting. Well, this is the good part. The bad part is that what happens is that the atmosphere can do strange things, because depending on the conditions, we can have reflectivity profiles maybe that do things like this. It diminishes, but then it increases, because at the end that depends on the content of water vapor, and that depends if there are clouds, and that depends on the weather conditions. Well, and under those circumstances, what we can have is a phenomena which is called ducts, and this is a guiding phenomena. And I'm just showing with a simulation here, in which imagine we have a transmitting antenna at 50 meters, and we are assuming this sort of refractive index profile. And well, we start sending rays, and of course, I'm assuming a flat Earth model. If I send a horizontal ray, of course, a horizontal ray does not see any change in the refraction index, so it propagates straight. But if I send rays with a certain angle, as the ray propagates, it bends toward the Earth, and here if I have a reflection, it goes up, it bends again, and so on. And if I send this ray here, I have a reflection, it bends, and then what I have is that for certain angles, I have a guiding of the rays. Of course, there are certain rays that eventually will escape and will come out, but there is that duct phenomena that actually between the contribution of the reflection of the ground and the bending of the rays due to the refraction can cause this guiding. Let me show you another example of this refraction. This is the sun rising, and you would expect to have a nice round sun, but you see that it's heavily distorted. And it's heavily distorted due to the refraction, because the rays traveling from the sun, depending on what height they are being radiated, they are distorted, and when we see the sun, we see this sort of distortion of the sun. So talking about summarizing atmospheric effects, well, for frequencies below 10 GHz, the specific attenuation due to atmospheric gases is smaller than 1/100th of dB per kilometer, so it's almost negligible. And rain can be the major cause of attenuation for frequencies around 10 GHz. Then we have to remember that we have those absorption peaks at 22 GHz and 60 GHz due to the water vapor and oxygen absorption. And then we have refraction that causes a ray bending due to the variation of the atmosphere refraction index with the height. And then in case of Earth to satellite communications, we have to consider that overall attenuation of the atmosphere, that of course it will depend on how we are pointing to our satellite compared to our zenith position.